Hi, I'm Herb Gross, and welcome to lecture number 18 in Gateways to Mathematics, where we again begin a two-part sequence called special functions. In other words, we're going to look at some special relationships. We'll start with some that we've already had and progress to some that are a little bit more, shall we say, advanced, but still yet very, very practical. What I wanted to do was to start over with something that we've already talked about quite a bit, and that's going to become known now in our new language as the linear function. In other words, this is the one that says f of x equals mx plus b, where m and b are constants, okay? And more specifically, if we say f of x equals mx plus b, we say that that's linear in x. See, in other words, the name of the variable isn't that important. All we're saying is if the input is going to be labeled x, then the output should be expressed in terms of x. If we had labeled that same input q, instead of talking about f of q being mx plus b, we'd say what? F of q is mq plus b. In particular, what you have to remember is whatever you put into this set of parentheses also goes into this set of parentheses. For example, if I had elected to put x squared in here, see, in other words, this would now look like what? Mx squared plus b. This is not linear in x, but it's linear in what? It's linear in x squared. In other words, the important thing is that whatever variable appears inside these parentheses has to be the multiplier of m. So we're going to deal with functions that are linear in x. In other words, unless otherwise specified, we will use x to name the input. So for example, we could have picked a relationship where m was 2 and b was 3. And basically, all this says is what? Whatever the input is, you double it and add 3. And that will give you the output. So one way of writing this would be, okay, we'll start with an input column, x. Then we'll multiply whatever the input is by 2. That column will then be called 2x. Then we'll add 3 onto that, 2x plus 3. And that will be what we call the f of x, or the f of x, or the 2x plus 3 column. So when x is -1, 2x would be -2. Adding 3 onto that would give us 1. See, notice how we're using our rules for sign numbers here. If x is 0, 2x is 0, 2x plus 3 is 3. If x is 1, 1 times 2 is 2, 2 plus 3 is 5. If x is 2, 2 times x is 4. Adding 3 to that gives us 7. And by the way, you can work with fractions also. If x is a half, 2x will be 1, and then 2x plus 3 will be 4. You see? And by the way, it may not even be a whole number. If x is 1/3, 2x will be 2/3. Add 3 onto 2/3, you get 3 2/3. And now if you want to think in terms of the graph, what you do is what? You list ordered pairs where the first member of the pair is the x value and the second is the f of x value. In other words, what I'm going to do is I'm going to list pairs with the first member coming from this column and the second member coming from this column. And this would now be called what? The pair -1, 1, 0, 3, 1, 5, 2, 7, 1/2, 4, 1/3, 3 2/3. And you see what that means is I can locate these points on the plane. In other words, 0, 3 means you're neither to the left nor to the right of the vertical axis, but you're 3 units up on it. See, 1, 3, it's 1, 5, I guess. Yeah, I have to read this. It means when you go 1 to the right, you go 5 up. 1/2, 4 means you do what? Go 1/2 a unit to the right and 4 up. 1/3, 3 2/3 means you go 1/3 to the right and 3 2/3 up. And -1, 1 means you go what? 1 to the left and 1 up, you see. And when you locate all those points, we see that they're on a straight line. And that straight line is the graph. So in other words, if you want to know whether a point is on this line or not, all it has to do is what? For whatever the x-coordinate is, the y-coordinate has to be 3 more than twice the x-coordinate. And by the way, the slant of this line, which is called the slope, is determined by any 2 points on this. In other words, I pick any 2 points, which I'll just generically name x1, y1, and x2, y2. And what the slope is I measure how high, in other words, what the change in y was, and I divide that by what the change in x is. In other words, I go from x1, y1 to x2, y2, and I compute what? y2 minus y1. That's how much y changed in going from y1 to y2. I divide that by x2 minus x1, which is how much x changed in going from x1, y1 to x2, y2. And that tells me the slope. And the slope basically, as I'll show you in a few minutes, measures how fast the curve is rising, or for that matter, falling. And by the way, when you pick x to be 0, the corresponding value of y, b, is then called the y-intercept. You see, when x is 0, y is 3. But what does it mean when x is 0? When x is 0, you're neither to the left nor to the right of the x-axis. That means you're on, you're neither to the left nor to the right of the y-axis. That means you're on the y-axis. And where the line intersects the y-axis is called the y-intercept. And you see, that's going to happen when x is 0. Now, by the way, people will sometimes say, which 2 points do you pick to compute the slope over here? What 2 points do you pick? Okay? Now, one way of doing this is to show people it doesn't matter what 2 points you pick. Let's go back to this page again, and we'll take a look. Okay? I'm just going to put my glasses on. I don't want to ruin an otherwise beautiful face, but the writing has blurred so much I can't see it too well without my glasses. Okay, here's the point 2, 7, 1, 5. In going from this point to this point, in going from 5 to 7, the change in y is 2. In going from 1 to 2, the change in x is 1. So 2 over 1 equals 2, and that's the slope. And what that means is what? For every 1 unit to the right you go, the line goes up by 2. But now a person says, what if I had picked 0, 3 and 2, 7? It doesn't matter. In going from 3 to 7, y increases by 4. In going from 0 to 2, x increases by 2. 4 over 2 is still 2. And what we're showing is that the slope doesn't matter, does not depend on which 2 points on the line you pick. In fact, we can go one step further over here and show this more dramatically. You see, what happens is, let's suppose I'll label these points in pairs. Suppose I had picked P1 and P2. Well, see, if I picked P1 and P2, I would compute this length divided by this length. If I had picked Q1 and Q2, I'd have picked this length divided by this length. Now, obviously, this length is shorter than this length, and this length is shorter than this length, but the amazing thing is what? All of these triangles, whether they're formed between R1 and R2, Q1 and Q2, P1 and P2, they all have what? Exactly the same shape. And since they have the same shape, it means everything will be proportional. In other words, the ratio of how much the curve rose to how far to the right you went will be the same in all these cases. And it also doesn't matter on which one you call the first point and which one you call the second point. For example, if instead of going from y2, instead of saying y2 minus y1 over x2 minus x1, suppose you had gone in the reverse order and pick y1 minus y2 over x1 minus x2. Notice that all that does is, when you reverse the order in a subtraction problem, it just changes the sign. You see, 5 minus 3 is the negative of 3 minus 5. And 2 minus negative 7 is the opposite of negative 7 minus 2. So what happens is, if you change both signs, negative over negative is still positive, nothing will happen. For example, suppose I take 5 minus 3 over 2 minus negative 7. What happens here? 5 minus 3 is 2. 2 minus negative 7 is the same as 2 plus 7, which is 9. This would come out to be 2 ninths. What happens over here? 3 minus 5 is negative 2. Negative 7 minus 2 is negative 9. Negative 2 over negative 9 is what? Positive 2 over 9, because negative divided by negative is positive. In other words, more generally, y2 minus y1 is the negative of y1 minus y2. x2 minus x1 is the negative of x1 minus x2, and negative over negative is positive, so therefore I can just cancel these out. Okay? So now what we have is, once we know how you find the slope, let's now talk about what the slope measures. If I tell you that the slope of a line is 3, it simply means what? The line rises by 3 units for every unit you go to the right. So if I started at the point P1 over here, and somebody said, draw a line through point P1, whose slope is 3, I would simply do what? Take any length I wanted horizontally, call that 1 unit. Then whatever that length is, I would mark it off 3 times vertically. See, I would go 1 to the right and then 3 up. Doesn't matter how long this 1 is, what this 1 represents. It's that what? Whatever length this is, this length will be 3 times as long. And so the ratio will be what? 3 over 1, or 3. In other words, if the slope is 3, it means the line rises by 3 units for every 1 unit you go to the right. By the way, I could have started the line at a different point, P2. Well, suppose I did that. I could still mark off what? 1 unit to the right, go 3 up, and do you see what's going to happen? This line and this line will be different, but do you see that they have exactly the same direction? In other words, if 2 lines have the same slope, all it means is that they're parallel, okay? And the way you use the slope and the y-intercept is that if you're given a line in the form y equals mx plus b, and suppose, for example, that m is 3 and b is 4, the b part tells you where the line is going to cut the y-axis. In other words, it's going to cut it at 4, 1, 2, 3, 4, okay? So that tells you the line is going to go through this point. The m part is 3. That means for every 1 unit you go to the right, you're going to go 3 up. And you see, once you know those 2 points, all you have to do is put your ruler down and draw that line. But if you want to do things more accurately, what you would also do is what? Compute 1 more point and make sure it comes out on the line. For example, if x were -1, 3 times -1 is -3. -3 plus 4 is +1. So I would try to make sure that the point 1 comma -1 comma 1 would be on this line, just to make sure I haven't made a mistake. By the way, the slope will not always be a positive whole number. Let me see if I can give you some more examples. See, suppose I told you instead of the slope was -3. See, 3 can be viewed as 3 over 1. -3 can be viewed as -3 over 1. By the way, there's no reason why I wrote it as -3 over 1, except that we're used to talking about going from left to right in the number line. I could also have written it as what? 3 over -1. And let me show you how you read both of these. This one says, every time I go 1 unit to the right, the line is going to do what? Drop by 3 units. So the line is going to be what? The direction of that line is going to look like this, the line that joins P to Q. Now, people say, well, what if I use this instead? Read what this says. This says, for every unit you go to the left, the line is going to rise by 3 units. See, I go 1 to the left, and y will increase by 3. So if I go 1 to the left, that brings me over here. And if I now go 3 up, I'm drawing this freehand. But see if you get the idea. See, in other words, I get this different point. But you see, this will all be the same straight line. In other words, either way, when I read this line from left to right, I'm going to see what? For every unit I go to the right, the line is going to drop by 3 units. It's traditional to read this from left to right. In other words, in this way, decreasing becomes identified with falling, and increasing becomes identified with rising. And aren't we used to saying the temperature is falling when it's really decreasing, and saying that it's rising when it's increasing? See, it would be strange to see something dropping and saying that it's increasing. And that's why, as we draw from left to right, we do the problem this way. But notice that if you're going uphill from left to right, it's downhill from right to left. And by the way, there are other examples. Let me just show you some more examples about the slope. How about the slope being 2/3? See, now what that says is, for every unit you go to the right, you go up by 2/3 of a unit. See, y increases by 2/3 every time x increases by 1. By the way, people who don't like fractions get intimidated by this. But remember, this is the top one is the y, the bottom one is the x. Another way to read this is what? Every time x goes 3 to the right, y increases by 2. See the psychological difference? Instead of saying the slope is that the line goes up 2/3 of a unit for every unit you go to the right, it makes more sense to say what? You go up by 2 units for every 3 you go to the right. And you see what I'm saying? In other words, if I go 3 to the right, I'm going up 2 units. If I only went 1 to the right, this would be 2/3 of a unit. But you see, by the fact that these triangles are proportional, this ratio is simply what? 3 this way to 2 this way. And by the way, the other problem that we're faced with is that sometimes the lines aren't given in this form. You see, sometimes what happens is you're told that 2x plus 3y equals 6. That doesn't have the y equals mx plus b form, okay? But it doesn't have to. See, what we can do instead is to say, look, let's subtract 2x from both sides. In other words, let's add negative 2x to both sides. The negative 2x cancels with the 2x over here, leaving us with 3y. And on the right-hand side, we have negative 2x plus 6. We want y by itself. Since the y is being multiplied by 3, we divide by 3. And by the way, dividing by 3 means the same thing as multiplying by 1/3. So y is 1/3 of what's ever in the parentheses here. So by the distributive property, the 1/3 multiplies the minus 2x to give me minus 2/3 x. The 1/3 multiplies the 6 to give me 2. And what does that tell me? It tells me that I have a straight line whose y-intercept is 2, okay, and whose slope is negative 2/3. In other words, what that tells me is that if I start with the point 0, 2, every time I go 3 units to the right, the line drops by 2 units. Now, there's another way of doing this that I think is very effective. See, instead of doing the problem that way, why not just find 2 points? The easiest 2 points to usually find on a line is by either letting x equal 0 or y equal 0. If we let x equal 0 over here, 2x then becomes 0. This says that 3y is 6. That tells us that y is 2. That tells us that we know that 0, 2 is a point on the line. Similarly, if we let y be 0, 3y will also be 0. This says 2x equals 6, hence x equals 3. In other words, when y is 0, x is 3. Now watch what we can do. We can now plot the point 0, 2. See, that's what? 2 units up on the y-axis. 3, 0, that's 3 units from the origin on the x-axis. Now with these 2 points, I can draw this particular line. And when I draw that line, notice what happens. You see the y-intercept did in fact turn out to be 2, and didn't this line drop by 2 units? In other words, it went from 0 to 2 as we went from 0 to 3. In other words, the line dropped by 2 units as we moved 3 units to the right, which verifies that in the mx plus b form, this is y equals minus 2/3 x plus 2. Both of these forms are correct. You use whichever one you want, but this is the graph, okay? Now, one of the other things I'd like to do in coming to sort of a conclusion here is to talk about something that's very important that we brought up with signed numbers, and that's the absolute value. Instead of graphing f of x now, let's graph the absolute value of f of x. Now let me show you how the absolute value works. Let's suppose I start at 0 and I go to the point P1. And now from P1, I come back to the point P2. Let's take a look and see what this means. In going from 0 to P1, I move 5 paces to the right. In going from P1 to P2, I move 3 paces to the left. So where am I relative to where I started from? I started at 0, I wound up at P2. Notice that the distance from O to P2 is 2 units, isn't it? In other words, I wind up 2 units to the right of where I started. But I didn't travel 2 units. Notice that I went 8 units. In other words, to get from 0 to P1 was 5 units. Coming back from P1 to P2 was 3 more units. So altogether I went what? 5 units plus 3 more. You see, if I just take these 2 and add them algebraically, positive 5 plus negative 3 adds up to positive 2. That tells me where I am relative to my starting point. But it doesn't tell me how far I went. See, to find out how far I went, I have to count what? The 5 that I went to the right plus the 3 I came back to the left. Remember, all the positive and negative does, it tells you what direction you went in. See, in other words, if you go 5 to the right, then you come back 5 to the left. You're right back at your starting point, aren't you? But it doesn't mean that you didn't move. It's like suppose you go around the circle 3 times. You come back to where you started from, but if you, in other words, you're not removed from where you started from, but if you're traveling in an automobile and you're using gasoline, you don't say, well, since I came back to where I started from, I didn't use any gasoline. No, just because you came back to where you started from doesn't mean that you didn't travel any distance. And sometimes in mathematics, it's more important to know the total distance that you traveled than to know the relative position of where you started relative to where you finished. So sometimes what happens is we want to talk about the size of the transaction, the size of the motion, rather than the direction. And just by way of review, notice that the absolute value of a number is just the size, it's just the adjective. So if somebody says, what's the absolute value of 3? Well, it's positive 3, isn't it? And the adjective part is just the 3. See, so if the number is non-negative, if n is non-negative, the absolute value of n is just n. If n is negative, see what happens? See, if n is negative, what's the absolute value? The adjective part is 3. The negative part just tells you that it was decreasing. In other words, this means what? A decrease of 3 units. What's the opposite of negative 3? It's positive 3. See, all we're saying is what? The absolute value is the size of the number. It disregards the sign. So whether the number is positive or negative, the absolute value is going to be positive. So in other words, if you have a large positive distance and a large negative distance, rather than them canceling and coming out to be positive 1, when you deal with the absolute values, this becomes 15, this becomes 14, and the answer is 29. In other words, you don't let increases cancel decreases when you want to find the total value. Now, the way this applies to graphing is very simple. Suppose I said to you, draw the graph of if f of x is 2x minus 3. Well, you see, this is the mx plus b form. Got to be a little bit careful over here. See, to put this in the plus form, subtracting 3 is the same as adding negative 3. So m would be 2, and b would be negative 3. Now, how do you graph that? It tells you when x is 0, b is negative 3. So this is your y-intercept. It also tells you what? That for every unit you go to the right, you go 2 up. So the slope would be 2. I would then draw the line this way, okay? And now that's the graph of the line f of x equals 2x minus 3. Now suppose instead somebody says to me, no, I don't want the graph of 2x minus 3. I want to know the absolute value. See, I want to graph the absolute value of 2x minus 3. Now remember, 2x minus 3 is going to be the same as the absolute value of 2x minus 3, provided what's inside the absolute value sign is at least as big as 0. Otherwise, it's going to be just the opposite. See, how does a y value and its opposite look relative to a graph? See, let's take a look over here. Let's suppose we look at this value of x. We come down here. That's the y value. See, notice that y is already negative. That's incorporated in here. What would the opposite of y look like? The opposite of y would be what? Exactly the same size, only in the opposite direction. In other words, to replace a number by its opposite graphically on the y-axis, just take a mirror and put it on the x-axis, and whatever you see in the mirror image, that's the reflection. You see, what's going to happen here is that every single point that was below the x-axis means it was what? Negative? So it's going to be what? It's going to be reflected that same distance above. So if you want to graph the absolute value of 2x minus 3, once you know how to graph 2x minus 3, all you do is put a mirror down here, and the part that's below the axis is going to reflect right up here. See, in other words, this line would be the graph y equals 2x minus 3. The graph of y equals the absolute value of 2x minus 3 would be what? This and this. And by the way, that works quite in general. Suppose the graph of f of x happened to look like this. You see, if I replace things by the absolute value, everything that's positive, see, everything that's above the y-axis stays the same. What happens is everything that was below the axis gets reflected above the axis the same distance as it was below. So in other words, if this was the graph of f of x, the graph of the absolute value of f of x would look exactly the same, except what? The part that was below the x-axis would then be what? Reflected relative to the x-axis. Reflected means what? The mirror image. So now the graph of the absolute value of f of x, in this case, would be like this. Now again, in closing this lecture, what we're saying is that as important as knowing a functional relationship is, there are times when signed numbers are used that we're much more interested in the sizes than we are in positives canceling negatives. It would be like a man sitting at home with his feet in the oven and an ice pack on his head. And people say, how do you feel? And he says, on the average, pretty good. See, you don't want to average out frozen feet with a hot head. In other words, the head is still hot and the feet are still cold. If you want to give that discomfort feeling that the person has, you have to look at both of these things separately and not just average them out. Okay? See, sometimes averaging is good, sometimes it's dangerous. So there are times when we're going to be interested in what? Just knowing the magnitude, the size of a signed number, and that's going to affect how the graph is going to look. But so far what we really did was what? All we studied in this relationship, in this lecture today, was the relationship known as a linear relationship, and we also did what? We looked at what happens when you replace the relationship by its absolute value. Next time we're going to look at a couple of important non-linear relationships, but that will be our next lecture. Until that time, as I say, have fun, study hard, and stay young. See you next time.